Yeah, welcome everyone in this great auditorium. On this evening, it's great that you're with so many today, and it's an honor for me to stand here representing the VVTP, the Study Association of Physics in Delft and Studium Generale Delft, to present to you our speaker of tonight, Erik Verlinde. Well, to you, he must be very well known, especially for his alternative theory on gravity. And he seeks to find an explanation for gravity that's consistent with both quantum mechanics and general relativity. And it's interesting because he's been interested in gravity, the smallest and the largest of the universe, since he was, I think, 15 years old, if I'm correct. Because then he watched a TV show, Sleutel tot het heelal, Key to the Universe, and he saw there his great examples, which are now his colleagues, I think, such as Gerard Hooft and Stephen Hawking. Well, then he studied in Utrecht, and he also did his PhD there. And he worked at Princeton, CERN, Utrecht again, and since 2003, he's a full professor at the University of Amsterdam. In 2011, he won the Spinoza Prize, which must also be well known to you. It's the highest science prize that you can win in the Netherlands. And today, he will take us on a journey through his research. So it might be hard sometimes, but bear with him. And after the lecture, which will take about an hour, there's plenty of time to ask all the questions that you want to ask him. There are catch boxes here. So wait, yeah, they're shown now. Wait till they are thrown at you, such that everyone can hear the question that you ask. So thank you very much for being here, and let's welcome Professor Erik Verlinde to the stage.
Yeah, thank you. Thank you for this kind introduction, and it feels very good to be here and to see indeed there's so much interest in this topic. I became interested, as Julia was explaining, already in my high school years, and I knew I wanted to do physics and in particular work on problems related to gravity and quantum mechanics. And indeed, we have made a lot of progress, and what I'm doing now, I could not have imagined that at that time, but it seems like we're finally starting to understand better how to put these two subjects together, because at the time when I started studying, it seemed like gravity and quantum mechanics were totally different worlds, and they couldn't be sort of united. So the current developments really have a new way of looking at gravity, a new way of even looking at the universe, and what are its building blocks. And I'm going to start out explaining a little bit why are we changing every time our point of view on nature, why is it necessary, and it has to do with experiments, with observations, but also with the language that we're using. Because every century in physics, there's a connection between what we do in terms of technology and what we do in science. We use the language of the world around us, and so in the 17th and 18th century, people knew mostly about mechanics of moving objects like, well, cannonballs. Then in the 19th century, we discovered steam engines, and then you talk about temperature, pressure, and maybe gas flow. Eventually, atomic picture rises. And then in the 20th century, well, a television, one of the technologies we developed then, if you look inside of it, it takes particles, electrons, it accelerates them, and then it lets them hit the screen, and then we get light out of this. And sort of the forces that are used are electric forces, things like that. Actually, that's the language of the 20th century. Particles, forces, and that is also still today very much the way we think about nature, as in terms of elementary particles and fundamental forces. But we live in a different time now. I mean, we have information devices. I mean, our current technology is based on what we can store in terms of bits, and we have a different language that's being developed. And this is what I'm going to explain, is that the basic building blocks even that we're going to use to describe nature are going to be not particles or the fundamental forces. We're going to think about something called information. And I'm going to explain more what I mean by information. You may think information is what you read in a newspaper, but for me it's something more abstract. It has to do with really the microscopic information that's contained in everything that nature is made of, even space and time. So what is indeed information? I mean, it's stored in bits, and this is sort of, for me, unimportant what is written there. You just count, for instance, how many bits you have, and that tells you how much information you in principle can store, say, on a chip, or even in other parts of nature, we can count information in terms of how many bits. I'm going to talk about special bits, not just zeros and ones. We also are going to use quantum mechanics, because microscopically, or actually the whole world itself, is quantum mechanical. So if you ask how does nature store information, it has to do it in qubits, not just ordinary bits. And qubits can entangle. I shouldn't be explaining this here, people know this very well. And this is the kind of thing that we're going to use and encounter also during the talk. So I'm going to tell you a new way that we're going to think about the universe, where we think about the basic building blocks as being information. This is maybe a way of phrasing it, that we live in an information universe, not an information world. The whole universe is revolving around information, and you may wonder, where is it and where are we going to, well, find it, because we may not be aware of all of this. And some of the information is hidden from us. And that actually brings me to another concept. I mean, if we have information we don't see, I mean, how are we sure it's there? First of all, let me show you this. You probably don't know what it is. But if I make it smaller, you still don't know it, but it's the same thing. But if you look at the bigger picture, you start understanding what that was. I mean, it's part of a picture that shows you now mountains and trees and all kinds of things that we can give names. But if you ask, do these things exist microscopically? No, because everything is made out of pixels. And it's only by making many pixels together that we get an image, and that we are giving names to objects, but microscopically these things may not be there. And this concept is called emergence, that when you build many things together, you see structures arising and you give it names that may not exist at microscopic level. And this is how I describe it. Indeed, we use concepts and we observe phenomena in a macroscopic world, at macroscopic scales, but they're derived from something microscopic where the same concepts are not well defined, and they have no a priori meaning. So we do this all the time in physics. For instance, statistical physics is a way of explaining thermodynamics. Thermodynamics uses concepts like temperature and pressure or entropy. But microscopically, those things don't exist. So the macroscopic properties are derived by averaging over all the microscopic properties. And so temperature can be defined as a measure of average energy, for instance, per degree of freedom or per molecule. Entropy then is associated with the amount of information that I'm actually forgetting when I go from the microscopic language to the macroscopic one. When I look at the room here, we're not really interested how all the molecules are moving, and we usually don't look at that, but we are interested in the temperature, the pressure, those kind of quantities. But eventually you have to also count what are the number of possibilities that are present for all these molecules. And that's measured by entropy. And actually this is the link with information, because what is entropy? It's basically the amount of information that's necessary to describe how all these molecules are moving. And it sort of counts the number of microscopic possibilities that are present, and therefore it's not an entropy that we can really, of an information that we can really read, but we can at least count how much there is. So the connection between entropy and information actually is due to Shannon. Shannon basically said that if I have a number of bits, that means zeros and ones, but it can also be coins, that you flip, you have heads and tails, and if you have 2 coins, then there are 4 possibilities. But then you can count the entropy, and that's basically taking the logarithm of the number of possibilities, and so that's then it becomes, in this case, equal to the number of bits. So that's an intuitive way of thinking about entropy. Of course, it doesn't always need to be in terms of zeros and ones or heads and tails. I can also use dice and then count how many possibilities I have here, but still you can count it, and this is how we associate the amount of information that would be necessary to describe all of these ways that these dice are being thrown in terms of an entropy. So for me, information is not, as I said, what I read in a newspaper or what is really useful. It's something that I can count and I can think about in terms of bits, or as I'll explain later, in terms of qubits. So what does this have to do with gravity? I'm going to tell you later that indeed we have a way of understanding gravity and its connection with information, and it's going to teach us something about the universe, and it's going to teach us something about how things might be different than what Einstein is telling us. So Einstein describes gravity in terms of curved space-time. I'm going to tell you that underlying that there is some information that is present and that will actually affect the way that gravity works. So let me start with Newton. Of course, you all know that the law of Newton tells us how the force between two masses acts as a function of the distance, goes like 1 over r squared. It's the same as how the surface of a sphere would grow as a function of the distance, namely it goes like r squared. This actually is already a hint that gravity has something to do with this area of spheres, or something like an r squared. And later I'll indeed show you connections with that, for instance, with how entropy arises in black holes. It's also associated with areas. But it's basically this 1 over r squared law that is telling us that. So this law tells us very well how planets move in the solar system, and it has been tested very precisely. If you look at how the velocity of planets behave as a function of the distance, Newton's equations would tell you that the acceleration is v squared over r is equal to gm over r squared. And from this I can read off that the velocity should go down as a function of the distance. And if you look at the planets, that is exactly what happens. Now, all of these planets behave very nicely according to Newton's law, except the most inner one has a bit of a problem. Normally, planets would go around like this in an ellipse orbit, where they have a near point, which you call the perihelion, and then there's the furthest point. But the perihelion should always be at the same location. And for Mercury, that doesn't happen. This is an exaggeration. There's every time that it goes around, it has a slight rotation, and in a century, it's like 43 arc seconds, I think that is. So this is a very tiny deviation, but it's a deviation from the laws of Newton, and you might try and explain it by invoking or postulating that there is some other planet closer to the sun, and that might actually cause this deviation to happen. And this is what people looked for, but that's not the explanation. It's not that we can save Newton's law here. This is in effect due to general relativity. So Einstein indeed could explain what happens to Mercury, and he could explain many more things, in particular also how light behaves in the presence of gravity. So according to his theory, gravity is the result of curvature of space and time. And so objects no longer go in straight lines, they go around in these elliptical orbits, and maybe small deviations from it that are due to the fact that indeed Einstein's equations are not exactly the same as Newton's equations. He wrote down an equation that tells us that in most circumstances Newton tells us very well what's going on, but in other circumstances when gravity gets very strong, we need Einstein's equations, and also to explain or understand what light does due to gravity. In particular, light can bend, and in this picture we see that light generally we think about as going in straight lines, but when there's a heavy object, then the light of an object that's behind the mass here can bend around, and we can see it, but we then see it at another location, because we would think that the light that is coming to us actually is coming from this star. So you see actually a dislocation or a displacement of the location of stars, and this is called bending of light, or you can have a certain effect we call gravitational lensing, which is sort of the same idea, that namely light bends around and can come to us, but it can bend around if there's a heavy object in the middle in more than one way. Actually, it can bend this way or that way, and even go above or below. And this is an example which indeed has really been observed, where there's a galaxy far away and there's a big mass in front of it, and then the light gets towards us in more possible ways. Actually, it forms a ring, and that's called the Einstein ring. And this is proof that light is being bent by gravity and can be explained by Einstein's theory. So Einstein has explained Mercury, he can explain bending of light. Of course, there are many more tests of Einstein's gravity. In particular, a very spectacular one which you heard about, which got the Nobel Prize last year, is the detection of gravitational waves. So where you can observe that space-time, according to predictions of Einstein, has ripples that are sent out when two black holes are colliding or merging together. In the last moment, they spiral so violently that the space-time itself gets distorted. And these ripples, they travel towards us with the speed of light and can be detected in this interferometer. This is one of the LIGO ones. And they were in two locations, well, about 1,500 kilometers apart, or maybe more even, where both found the same signal at the same time. So this is what happens. I think you can hear it. Can I? No, the sound. There should be sound. No. Okay. There is a sound of this that allows you to hear what is going on. It's actually a ringtone that you can buy, which is indeed the detection of these waves. So this is indeed Einstein's equation, and here are the ways it has been tested, and in many more circumstances. So gravity waves, there was already indirect evidence of gravity waves from binary pulsars, bending of light, and what happens with Mercury, and many other ways. So you might say, well, this theory works, and it seems to work in many circumstances, but does it work in all circumstances? I'm going to actually tell you something about larger scales. And here you might say, well, it should work as well, because we don't know anything else. Einstein's theory must be right, so we're going to look what it does. But does it really look the same? So when you look at galaxies, they look in a certain way like a solar system, in the sense that most of the mass is in the center. If we look at the stars, there are many more in the center, and you can think about all these stars as going around in sort of circular orbits, where you can look at each of those slices and ask what is the velocity. You can measure this by redshifts, and then you see, as a function of the distance, you would have expected from the same way that planets behave, namely that at large distance the velocities go down, that it would do something like this. But this is what's being observed. Now, you can have two conclusions. Either you say gravity works in a different way, or if you assume that Newton's law should work, there must be something, well, explaining this difference. Well, what's happening here is that the stars are moving much too fast, and they would, well, fly out of orbit if you rotate too fast with not enough force. And so there must be additional force pulling it together, otherwise we cannot explain why these stars would go so fast. And so there must be additional gravity. So this is another picture of it. So this is what's called a rotation curve. So this is the velocity, and this is, again, the distance. And this is what you would expect, and this is what we observe. Actually, in most of these galaxies, the following thing happens. Instead of going down, the velocity stays constant. It's called flattening of the rotation curve. And there's a big difference between what is expected and what's being observed. And there must be more mass, actually, if you want to explain this. So this is indeed different from this equation. Actually, you can determine what should be the additional mass by looking at the velocity and using this equation. And this is what led to the idea of dark matter. It's a hypothesis. It's very much like what a planet that was assumed to be there. Namely, it fixes Einstein's theory because we say there must be more mass and we would look for it. And there must be some particle that is forming a cloud, a sort of a halo it's called, around the galaxy, where the gravitational force which is needed to keep the galaxy together is obtained from the additional mass that's in these particles. These particles cannot be seen. Here they're blue, but that's just an artist's way of showing it. But the particles have no interaction with light. They should be only gravitational, have only gravitational forces. Well, people look for it in accelerators. They look for it in the detectors under the ground. And so far, nothing has been found. And so you might wonder, is this the way, indeed, we have to fix Einstein's theory, or is there another explanation? As I will explain, there are more things we don't fully understand in cosmology. There's also something called dark energy. I will return to that later. So there will be questions that we need to pose and need to answer also, well, at large scales, that might actually tell us that something else is going on than what Einstein might have written down. But for me, the main motivation, actually, of main indication that Einstein's theory might work differently comes not from these observations, but also from theoretical well, developments. I mean, indeed, the work of Hawking, which is the one I already became interested in, his work was on black holes in particular, and indeed on cosmology. But black holes is one of those topics that we theorists use a lot to learn more about gravity. So what are black holes? These are predicted also by Einstein's theory. This is where mass is put together in such large quantities and so close together that light cannot even escape. I mean, gravity becomes so strong that from a black hole there's no escape when you go too close to it. There's namely some imaginary sphere around it, we call this the horizon, that if you go inside that sphere, then you have to go faster than light to escape, and since nothing can go faster, you cannot get out, and light cannot even get out, and this is why the name was given black holes. So we know that mass goes in, so we know the mass of a black hole. Black holes can rotate, but otherwise we have no information of what's inside the black hole. So everything we throw in disappears from our view, and so black holes are really objects that we can only study from the outside and wonder what went in. So this is what it looks like in terms of the space-time. So a star like the sun would have a curvature of space that looks like this. It sort of makes a dent. You can think about this as a sort of a rubber sheet where you put a ball inside and then it sort of bends through over, and so it has some dent in it. And the more mass, the more you concentrate it, the deeper it goes. And in a black hole, there's a sort of a funnel. There's a hole coming in that goes all the way to the bottom, or at least it goes so deep, indeed, that you hit this imaginary sphere, where's the horizon. So all the matter goes behind that horizon. So this is how we should think about black holes, is namely that all the matter has sort of disappeared, and only what's left behind, what we can see, is the space-time, the curved space-time of the black hole itself. So what would it be if we would be in the neighborhood of a black hole? Here is the Earth, and this would be a black hole, and this is sort of what you would see. It sort of looks like the Earth is being distorted. That's not actually happening. This is the light that we see, namely the Earth is just rotating around the black hole, but the light is coming towards us from all directions in the way that this gravitational lensing worked. And so we see the Earth sort of going in this circle. But of course, it's just rotating that way. I can also show you what it looks like when we fall into a black hole. And then I want to remind you of this bending of light. So what I'm going to do later is show you a little clip of how we move inside in the neighborhood of a black hole. The horizon is this red line. We're going to look at the black hole, which is here in the center, and we're going to look at the light coming towards us. So the light here is some background, which is the galaxy. But this is going to move. We're also going to watch what happens with the clock, because black holes have another special property that not only light cannot come out, also time behaves very differently. So Einstein's theory does not only change space and curves it, also the time goes very differently in the sense that actually clocks are going slower when you go close to the horizon. Actually, it really stops even when you're on the horizon. And so we're going to watch this when we look at the movie. So here's the same picture again. So we start out from this distance, and now we're going to fall. And the green region is where we can travel safely. You go around in these closed orbits. When you would go closer, here you would need a rocket to stay safe. But when you get to orange, there's no way to get out, because then you will fall into the black hole, which is where you have entered the black hole. So here we're getting closer. We see also the horizon eventually. That will be indicated with the red lines. The north and the south pole are a little distorted because of the bending of light. Here we see indeed the light. There's one distance where light itself can even go in a circle around it. So light would even be captured by a black hole. And here we indeed see the clock going slower. And at some moment we cross the horizon, and then we see indeed the last sort of light coming from outside. And nothing is shown what's coming from inside, because basically we don't know. So eventually we hit the singularity. That's what's in the center. So the center of a black hole is where curvature is so strong that we really don't know what happens there, because even Einstein's theory breaks down. But most of the interest actually of theorists is on the horizon. And so that horizon, I can actually show you this clip once more. Most people want to see it twice. So this is the same picture again. And as I said, I mean, there is a singularity inside, but the horizon itself is a very interesting place because of the way that the time indeed seems to stop from the outside. But when you fall in yourself, you actually don't know that you're crossing a horizon. I mean, the space actually looks pretty normal. Yeah, you get strong gravity, but it's not like there is something really infinite or something. No, there's really normal space. So you could fall in. The only thing that goes wrong with you is when you hit the singularity, or when the gravitational field becomes really strong that it pulls you apart. But the horizon itself can be analyzed in a very similar way as we analyze other parts of space-time. And this is indeed what Bekenstein and Hawking did. This is a more precise picture indeed of this space-time around a black hole. So a black hole has the property that there is one distance which we call the horizon. Here we draw the space actually as if it's two-dimensional. So the horizon normally is a sphere, but here it looks like a circle. And when you would emit light, it would normally go in all directions. But in this case, when you're on the horizon, all the light actually goes inward. And this is how you would indeed fall in if you cross it. Now, Bekenstein and Hawking were worried about the laws of thermodynamics, and in particular what happens with the entropy of objects that you throw into a black hole. Namely, this entropy is disappearing from our view. It represents a certain amount of information, I told you this, and what happens to that information? Well, if we throw it into the black hole, it disappears from our view, and so you might say, well, this entropy disappeared. Indeed, you can do thought experiments that allow you to actually generate work by throwing in this matter with all the entropy in it, and then you would even have a way of generating work and actually violate the laws of thermodynamics, because the entropy would not go up. I mean, it would actually go down. And so the only way to save this was to associate a certain amount of entropy also to a black hole. Now, this was the idea of Bekenstein, and Hawking then came along, and, well, he first didn't believe it, because if you have an object that has a mass, which is also an energy, E equals mc squared, and it has an entropy, then it also should have a temperature. And Hawking was not convinced that this would be possible until he realized that he could actually calculate it. And this is how he found the famous formula. So actually, he found that black holes emit radiation. I should first explain that. He actually found indeed that it has a temperature. It's called the Hawking temperature. And he found that by quantum effects, because both of these, Bekenstein as well as Hawking, reasoned that we should use quantum mechanics to explain this amount of information associated to the horizon. And indeed also the temperature involves quantum properties of well, particles and of space and time. So in particular, particles in the vacuum can exist even if the vacuum normally you think is empty. Because of the quantum uncertainty relations, the vacuum contains what we call quantum fluctuations, means that some particles and their antiparticles can be present for a very short time and then they usually recombine again. This is this picture, but when there is a horizon, what happens, and this is what Hawking showed, one of the particles can disappear and go inside the black hole, and the other is being emitted and comes out as a particle that we can detect, and it has a certain temperature, it's radiation, it's like black body radiation with a temperature set by the acceleration actually at the horizon. So these are the formulas that Hawking derived. So the temperature is given by the acceleration, the gravitational acceleration, that's g, at the horizon. So this formula is just the same formula that you know from Newtonian mechanics. This is the acceleration at distance r. M is the mass of the black hole. The radius, by the way, is set also by the mass. I mean, this horizon distance, we call this the Schwarzschild radius, is also determined by the mass. Bigger black holes, actually this radius becomes larger. It's actually proportional to the mass. But if I calculate this and put it in this equation, I would get the temperature, and that is indeed the Hawking temperature that Hawking calculated. I said it has a temperature, but also an entropy, and that formula is also famous, and it's known by the names of Bekenstein and Hawking. Here I show it in a picture. I'll show you the formula in a minute. So we think about entropy as information, so zeros and ones. And you may ask, well, how much information is then stored by a black hole? It's given by the area of this surface of a sphere. And namely, you have to measure it in Planckian units, very tiny units. And then if you put zeros and ones on all of those locations, you could store an amount of information, and that amount of information is the entropy or the information that black holes carry. And in a way, it hides the information because we cannot see it, but we can still count it in terms of an entropy. Here it's explained how large it is. It's 10 to the minus 66 square centimeter. So there's a very tiny surface. And this is indeed what the formula looks like. So the entropy, which is called S, is equal to the area of the horizon divided by the units by the Planck scale. And this is written down in natural units containing Newton's constant, Planck's constant, and the speed of light. And if I would have all the units right, actually entropy has the dimension of Boltzmann's constant. So all of the constants of nature basically enter in this equation. And so this tells us how many bits information is associated to a black hole. And this was a very important discovery. Actually, it led to many discussions because the question was, well, does this mean that we can still keep track of this information and can we retrieve it? Bekenstein, in particular Hawking, actually argued that information is lost in the sense that information that we throw into a black hole cannot be retrieved, and it would violate even the laws of quantum mechanics. So Julia already mentioned the people that I watched on this show were Hawking and Ed Hooft. And Gerard Ed Hooft actually, when I started studying, started worrying about this problem. And he started arguing with with Hawking about this information loss paradox. Are the laws of quantum mechanics obeyed, yes or no? Because if quantum mechanics is obeyed, actually quantum mechanics, it works in such a way that it doesn't really destroy information. We call this unitarity. I mean, probabilities have to be preserved, but also information that's in a quantum state cannot simply disappear. So in order to save quantum mechanics, we have to understand what this information represents and how it, we may even retrieve it. Because when the particles are being radiated out, the information has to be sort of released from the black hole. And it's up to this day that people are still discussing it because it's very hard problem to solve, but it teaches us a lot about how space-time, how gravity works, and what the link with information is. In particular, indeed, that this information is stored sort of on areas on a surface, say, of a sphere. These are some more complicated equations. Actually, I show these equations because we actually use them a lot. And what they show is that the gravitational equations, the one that follow from Einstein's theory, actually they are basically the Einstein's equations. So what I've shown here is the formula that tells you how much does the area change when I change the mass of a black hole. It's determined by the acceleration at the surface of the horizon by this equation. So you might say this equation follows from actually Newton's law or even Einstein's law. Actually, you might say this is of Einstein's equation. It's a way of summarizing Einstein's equation for black holes. And therefore, you might think it's a fundamental equation. But when we make these substitutions, namely we say the area is the entropy and the acceleration is related to the temperature, then this equation is the same as that equation. And that's the first law of thermodynamics. And that is a law that we can derive. We can derive by thinking about statistical mechanics and understanding what this entropy is. We can derive this equation. So if we understand this entropy, we can derive this equation by statistical mechanics. But then we have derived Einstein's equation. And that's the idea of what's called emergent gravity. Indeed, that gravity itself can be explained microscopically once we understand what this information represents and how we then can derive these laws. Because then we derive Einstein's equations from a more fundamental microscopic picture in the same way that we have explained the laws of thermodynamics by thinking about atoms and the way they behave statistically. So that subject has been actively studied now, in particular the last number of years. I'm going to tell you a little bit more about what is going on there. But this is really the way that we think that we have found a crack in Einstein's theory, that there might be a way of thinking about gravity in a different way than that Einstein told us, by thinking about the microscopic structure of space-time, not in the language of particles, not directly in the language of forces, but thinking about more fundamental building blocks in terms of information, and in particular its quantum properties. So 't Hooft indeed was one of the first people to start thinking about the implications of what we learned from black holes, and he already made a very important conjecture, or basically stated a principle. It's called the holographic principle, that there's no way that in any region of space you can have more information than what is given by a black hole, and means also that this amount of information cannot be larger than the area of the surface around it in Planckian units. So if I take this big lecture hall and I ask what's the maximum amount of information we can store here, you might say I put a very big computer here with the smallest chips possible, but that information can never exceed what you can put on the boundary in terms of Planckian bits in terms of its area. Because if you would basically form a black hole as large as this room. So that's the state of maximal information, and there's no other possibility. So this was an idea at the time, but it has been made much more precise and actually been realized in string theory. I'm not going to explain a lot about string theory, but I'll say some other things later. I want to tell you a little bit about how I started thinking about these ideas some years ago. In particular, indeed, the idea of what's now called emergent gravity. Can we derive gravity by thinking about this information? Can we indeed derive Newton's law, for instance? And by assuming that indeed all the information associated with a part of space-time is counted or stored on the sphere of a surface around it, you can actually do so. You don't need to have much, math, or even, there's some steps you have to do where you make some assumptions, but then you can actually derive Newton's law. Actually, it's in a paper I wrote on the laws of Newton and on the origin of the laws of Newton and of gravity, where I derived Newton's law by thinking about a thought experiment, indeed by asking the question, what is the amount of force that you can derive by thinking about information stored on a surface, and ask, well, what happens when I put a mass close to it? Actually, I'll show you the equations in a bit. There's actually this slide I should have shown. So this is actually a calculation. I'll I'll go a bit through the steps. There was one assumption about where I say that the amount of information is indeed proportional to the area. That's this equation. I'll call that area measured in terms of Newton's constant. I have to assume that there's a force law that actually comes from the change of entropy. It's called an entropic force. You can calculate that change of entropy by a very simple thought experiment that tells you that there's only one bit of information associated to a shortest displacement. Anyway, it's not my idea to go through all the steps, but it's with some simple equations that I could derive Newton's law. So this is a way in which the idea of having gravity come from information actually could be realized. And since I wrote that paper, a lot of work has been done. And actually, we know a lot more now. And we have made, well, progress even in deriving Einstein's equations from quantum information. So what is this information? We want to know more about what is the information associated to the horizon and what kind of information is it. And as I mentioned, string theory, a big subject that I'll just have to skip because of time, actually has realized this holographic principle, but it also has led us to a conclusion that we can indeed explain gravity, but the information we have to use is called quantum information. So it's not just zeros and ones, as sort of all these pictures show. It's something different, associated not to bits, but to qubits. So let me explain a little bit about that development. So what is quantum information? There we have to distinguish indeed a bit from a qubit. A bit can be 0 and 1, but qubits can have superpositions. And you can either think about an electron with a spin up or a spin down, or just a state that is in between a 0 and a 1. So in a picture, a bit has only two choices. If I would have a certain probability of having 0 and a probability of having 1, you would have a sort of like a parameter that's the probability. But actually, in quantum mechanics, we also have complex numbers here. Actually, if you then count all the possible ways you can put 0 and 1 together, they actually form a sphere. It's called the Bloch sphere. So I'll actually make a picture of a qubit as a little sphere. Instead of having only choice 0 and 1, we have all kinds of choices in the middle. So this would be pure 1 and this is pure 0, but then there are other things in the middle that form this qubit. And this is the reason actually why we can store much more information on a qubit, or actually do even better calculations than in normal bits. The other property that makes qubits very useful is called quantum entanglement, where you have the problem or the possibility of measuring something in one location, and then the outcome of the measurement, which is, well, probabilistic. Actually, it's not determined directly, but it gives you one outcome. It determines the outcome of the other measurement, and that is called entanglement. So this is what I meant by this notation. There's some way that if you measure 0 on one, the 0 must be on the other, or if you measure 1, that's here as well, or in terms of a quantum notation, it looks like that. The people that thought about quantum entanglement the first time were Einstein, Podolsky, and Rosen, already in the 30s, a long time ago, and they worried about it because it had its strange action at a distance. But it's only much later that we start realizing the importance of what they did, actually, in the sense that entanglement was not recognized in the beginning as very important, but later on, and actually in recent years, this has been, well, the most important thing about quantum mechanics. And this kind of state is therefore called an EPR pair, named after Einstein, Podolsky, and Rosen. So we're going to use this kind of language also now to think about these information bits that are associated to horizons and to black holes and even to space-time itself. So we're going to think about entangled qubits, and I'm going to draw a picture of it. So this was one qubit. An entangled qubit can be thought about as two qubits that are connected by a little line, because actually the measurement that you do on one determines the outcome on the other. So it's something like a glue. Like the way we put molecules together, we can actually put qubits together by entangling them. So then what is this information? The answer is entangled quantum information. And I could have known this from the way that Hawking did his calculation. So Hawking did his calculation by thinking about how in the vacuum pairs of particles are being produced a particle and an antiparticle, but if they are being produced in one state, since this one has spin up, then this one must have spin down. So they're actually entangled. And so this is the way that indeed the horizon entropy is being built up actually from entangled particles. Because even entanglement, by the way, you can count how many of these EPR pairs do I have. So in this EPR pair, I have one bit here and another bit on the other side that are being entangled with each other. So I can count how many bits are entangled. So that's an entropy. And this is actually a more technical way of showing it. This is actually the calculation that Hawking did. Hawking showed that there is some energy eigenstates on the left and on the right which have a very particular way in which they are entangled. So this is what the horizon looks like in special relativity. And then you have sort of two states on the left and the right. This is just to show you that there's really some meaning to the entanglement, because this notation you should compare to what I had here. And then we can basically count how much entanglement is in this. Actually, it's given by the area of this horizon. So this idea that entanglement has something to do with gravity even has a name now. And the name actually goes back also to another paper of Einstein. Around the same time, he worked on horizons of black holes. It's this picture. If you have a black hole, I showed you there's a little curvature and there's some tunnel where you go through, but actually when you extend the Einstein equations and look at the full solution of the equations, actually there's another space that opens up where the black hole forms a wormhole that exists for a certain amount of time. It's called a bridge. Actually, it's called Einstein-Rosen bridge because he wrote that paper together with Rosen, the same Rosen from Einstein-Podolsky-Rosen, and they found this solution. Of course, they didn't know anything about emergent gravity and so on, but now in our present day, we have actually made a connection between this entanglement idea and the way that space is sort of built in this way. And this is called ER as EPR because it's basically telling us that indeed the entropy that we're measuring here is entanglement entropy, and it's counting all these qubits, and we sort of gluing space-time together through entanglement. This is a big development that's going on in the US now. Now it's called IT from qubit, where we built everything from information qubits, even space-time itself, and we have a different view of thinking about it. So now I have to hurry a little bit because I want to go back to the questions I raised in the beginning and hopefully explain a little bit what we can learn now about these problems that we are observing in cosmology from this idea. So what is the idea and what's the conclusion that I've given you sort of up to now is that indeed we can think about space and time as being sort of derived or built up from entangled quantum information. Even gravity comes about. But can we think about links with observations? So I told you about the observations in galaxies that we don't understand. And actually all the observations that are associated to dark matter in total. This is a way we have already determined that there's more gravity out there than we can observe. This is called a weak lensing in the sense when people can measure how much gravity there is by looking at this bending of light. And they've determined that there's a lot of gravity here, but most of the matter is actually in this region. And so we have seen sort of, well, locations where gravity is there without having matter. So this is where there must be something, well, like dark matter. Dark matter also forms an important role in the structure formation in our universe. So people believe in this a lot. But now, if you look at what the universe is made of, the ordinary matter that we see is only 5% of what we observe. And dark matter, according to the current observations of particularly the cosmic microwave background, is about 25%. But most of the energy in our universe is what's called dark energy. So this is 95% we basically don't understand. And we wonder what is happening there. So this little yellow line is actually the light that comes from the microwave background, the earliest radiation we can observe. And there are photons, and that's a very tiny number. But if we ask, according to our current theory, where most of the entropy is sitting in our universe, It's not here, it's not there, it's not there. It's actually in this yellow line. People don't assign any entropy to dark energy. They call it the cosmological constant. They basically forget about all of this. And our current theory only describing this a little bit. And this is where we have, I think, made a mistake, and I'll tell you a little bit what the idea is. So the way that people observe the universe, we do it from our center. We look outwards, and we see this radiation coming from large distances, because when you look further out, actually you go also back in time. The universe is expanding, which also makes clear that things are moving away from us. And there's a furthest distance we can look. And in a way, that gives us, just like for black holes, also a horizon. So to think about it this way, if things are a certain distance, they move away with us with a certain velocity. But if we go further out, eventually there will be a distance when it starts moving with the speed of light. And that means that the light cannot travel towards us anymore. And that's a distance we call the horizon of our cosmos. So in cosmology, we can describe this in terms of Hubble's law, which tells you indeed that the velocity goes with the distance, and the constant in front we call Hubble's constant. And so the distance where this velocity is equal to the speed of light is called the horizon distance, and that's measured in terms of this constant h. Now, why do I talk about this horizon? This horizon has very much the same properties as black hole horizons. And I told you horizons have information. So we can use here sort of an holographic idea of how much information can be put inside our universe. So if we would think about our universe as a very large computer where we store a lot of information, how much can there be in there? Well, not more than the horizon of this area, the area of the horizon. And that actually tells you exactly how much information is contained in the universe. So I'm going to actually tell you that this may affect things that are going on inside. Because I actually want to explain where this difference comes from. So the idea will be that this information associated to the horizon actually will not be just sitting on the horizon, but also in the center, or actually over the entire universe. So the following observation I want to explain. I told you that galaxies rotate, but then their velocities don't go down, they stay constant. But this happens at a particular acceleration, always the same value for all sizes of galaxies. So this is an acceleration according to Newton's equations, but I can express the value where this starts happening in terms of the Hubble constant. If I multiply c, with, the Hubble constant with the speed of light, actually it's an acceleration, and this always happens when this, when the acceleration drops below this value, this is actually when this starts flattening. And this seems like galaxies know something about the Hubble constant. Actually, it knows something about even the dark energy in the universe. So indeed, this is the picture again. So this is where this galaxy is sitting. And this is our cosmological horizon. It had this distance, this size. And it has an area that we can calculate. It's the area of a sphere. And we can calculate the entropy. We can also calculate the temperature according to Hawking. It's also given by a Hubble constant. And I say this entropy and temperature are actually due to the positive dark energy, and actually are carried by the dark energy, and they fill the entire universe. I think I need about, okay, I have 5 minutes? Okay, then that's about what I need. So this is where I write the same equations as I had for black holes, a temperature and an entropy. And it's an entropy we have not considered. Actually, it's a very low temperature. It's also a very low, but it's a very high entropy, I should say. This is a number which is called about 10 to the 120, while the amount of entropy that we have used for, say, photons is about 10 to the 90. So most of the entropy is actually sitting here. And actually, it's going to change the way I'm going to think about these galaxies. Here are some pictures of phenomena which look very similar. You probably can recognize that this is the galaxy, this is a hurricane, this is a whirlpool. The reason I show these pictures is that here we have water around it that's swirling. We see only the foam. Here we have air going around, and we see only the clouds. But we know that there's something in the middle that makes this happen. Here, we assume that it's just space-time, and that this is rotating without anything around it, because it's empty. Maybe it's not, and that's actually sort of the analogy that I want to make here. I want to tell you another thing. I mean, we have been observing the universe for a very short amount of time. So if we put the entire age of the universe in 1 year, humans came into existence 1 minute before midnight on New Year's Eve. And the amount of time that we've been observing the universe is about a fraction of a second. But we have concluded a lot of things about what happened in that entire year. But this is not always possible. I want to do one experiment with you, if I succeed, because it's a little bit tricky. Yeah, let me actually first do it this way. This is a bouncing ball, and I can calculate that it bounces, and it bounces every time the same height. So I know the theory of this, which is elasticity. I'm going to do this again, and it's going to do exactly the same thing, but the material is slightly different. Oh, I have to make it round. Actually, it does exactly the same thing. But if I put this here and I wait, this ball will stay round. This one will change. Actually, it's silly putty. It's actually a material made out of polymers. And if I wait long enough, it will start flowing. The only way I can know this is by waiting. If I would have measured it only by bouncing, I would have drawn conclusions. I would have developed a theory of this thing, which is identical to that one. But the physics is very different because we have to observe it for a very long time. So if our universe has properties of that, we have not been able to even test this because we have made observations for a very short amount of time. And actually, this is the analogy that's quite precise. And so the picture that I showed you in the beginning about a universe filled with information, that information is actually the information that I associate to dark energy, and it's filling the universe. I know exactly how much there is because I know the size of the horizon. I can calculate the information density. There's also an amount of information I can calculate associated to mass. Actually, this is a calculation that Bekenstein did already a long time ago, and I can compare the two, and then I can actually explain that something starts happening exactly when these rotations, the curves are changing. Actually, this is a paper I wrote last year, where indeed I made a calculation of what happens when mass is present in a universe with dark energy or without. And there's a lot of difference in the sense that the dark energy actually contains much more information, and you get sort of a back reaction, which is due to an elastic force. Actually, the mass is very similar to what happens in this material. And I can derive an equation that actually explains exactly this behavior. It behaves effectively as if there is some additional matter, but it's actually some additional force that's pushing the matter back. So this is actually what's being indicated here, is that there's actually an additional force due to the fact that the matter actually pushes away the dark energy. And that force effectively actually behaves like dark matter, and it explains these flattening rotation curves. It can be compared to data. Actually, this is measurements of this relation that I found. So what is plotted here is actually the acceleration that is observed. So the acceleration that observed is this one. And the mass that I put here on the right-hand side is the stars. So I've not put in anything of dark matter, but I can derive the acceleration here from only knowing the baryons, the stars. And then I can explain this rotation, the change of these velocities. And this is even actual data that show the same relation. It's called, actually has a name, it's actually this equation. It's called the Tully-Fisher relation, or mass discrepancy acceleration relation. And there's also measurements that were done in Leiden by Margot Brouwer using, well, not strong lensing, it's where you have bending of light, She used weak lensing, is where you sort of distort background galaxies. You can figure out the gravitational potential. And she found nice agreement with the predictions of the theory that I wrote down actually are the blue lines, and they fit the data very nicely. There's unfortunately some errors still in the data, but that hopefully will be reduced. So this is where to make clear that these theoretical ideas actually connect to data, and there might be some observational confirmation, because this is still sort of after the fact. You might say, well, I knew that these things should behave like that. So the challenge will be to make a prediction that has not been verified, but then you can indeed test things in our universe. And so this is sort of the last picture I want to sort of leave you with, is that my way I view that we have sort of changed the view of our cosmos is that our normal language of matter, forces, and space-time is one that is sort of 20th century. We have sort of changed the language where we want to understand things like dark energy and dark matter. But in order to explain it, we have to indeed understand how these things emerge. And then suddenly you sort of find that there's much more information present, which is sort of present in this dark energy, and it can explain the phenomena that we associate with dark matter. So this may be a way of sort of visualizing the ideas I've been explaining. Thank you.
Yeah, thank you very much for this. Thank you for this very interesting talk. And I think it's actually sad that we humans started to look at the universe so late. Maybe we need generations more to understand that we are actually maybe a fluid. And I think there are many open questions that you would still like to work on, but I think it's first time for questions of you to ask to Professor Verlinde. And the catch boxes will go around, so who wants to start off? Oh, there's already a question here in front. Maybe you want to send it.
Hi, I just wanted to ask about something that is there any super intelligence that is controlling everything? And it's such a basic question because I'm not from cosmology, but it's such a basic question that how the universe existed and how close are we in knowing the theory of everything.
So it's maybe two questions?
There are two questions, and I think they're kind of related. I have to say that I think it's already surprising that we've come this far as humans to understand the universe around us. But it's partly to do with the fact that we are very good at making things abstract in equations that we can handle, but in doing so we ignore a lot of information. I think we're smart, but I don't think we're infinitely smart. So for me, the idea that we can have a theory of everything that really explains everything is sort of hubris, in the sense that I don't believe that. Are we the only intelligent creatures in the universe? I don't know, I don't think so, but I cannot prove it. But I don't think we need to assume anything about that. Does the universe itself have an intelligence? That's the other question you're asking. Yes. I told you there's a lot of information in the dark energy that I have no idea of what it's doing or what is happening there. And it might have some collective behavior that you might define in some way, but I don't think it's important for us. I mean, so I don't even want to go into the direction of religion or this kind of thing, because for me that's philosophy. What I can do with my equations is only estimate how much information is there, what it's doing, and for us that's enough. And so I don't think that that question is part of what we need to answer as physicists.
Thank you.
Thank you. There are also questions in the back. I don't know where the other catch box is. Oh, there's already, yeah.
Hi, my question is, how do you measure or calculate the mass of a black hole that you mentioned through your equations?
How do you measure and calculate
Measure or calculate the mass of a black hole. One of your equations had the mass and the area relation of a black hole.
You want to know the relationship between the mass and the radius or something?
How do you mentioned the mass of a black hole, right?
Well, the mass of a black hole is something that you can measure on the outside, because the gravitational field of a black hole is far away the same as what would follow from, say, Newton's equations even. So if you measure, so how do we measure the mass of a star? We look at the planet nearby and then we look at the orbit. There's a direct relationship between how fast that is and the mass of the object in the center. So we can do the same thing. We just determine the gravitational pull of the black hole, and that actually tells us what is the mass. So actually they're close to doing this for a object in the center of our galaxy. There's a big black hole, and another star is moving closer, and what they're going to do is actually look at how it behaves. And one of the things they're very excited about is that they now discovered this star has no companion. We can do very precise measurements and can even determine the corrections to Newton's equations there. But one of the things we determine very well, therefore, is the mass of this object. It's just by looking how other objects in the neighborhood behave.
Okay, thanks.
Then I don't know where the other catchbox went. Here in front are some questions. In the back there are more.
Thank you for the
there's
lecture.
Yeah.
So
Where
you said
I'm looking.
here. You said you proved Einstein's equation by using analogy to entropy and probability concepts. Is it ironic that Einstein himself would have said that God doesn't play dice?
I still think that Einstein would have liked this way of thinking about gravity if he would have lived nowadays. It's true that his way of thinking about quantum mechanics and the fact that he tried to discredit it by thinking about entanglement, that it sort of backfired in the sense that entanglement now is being used everywhere and sort of almost as a proof of quantum mechanics that it works the way that people say. So anyway, I think Einstein was visionary and he had many clever ideas and many of them still come back. And I don't think he would be unhappy if he would be still alive and see this.
Well, this may be an interesting addition is that I tweeted this lecture today and there's a picture of you, I think, where you have your hands to the back. So people said, oh, it's so sad that it's a lecture and not a fight.
Oh.
And then people started to make this epic rap battle. Do you know about that? Between you and Albert Einstein, actually. So they appeared on Twitter now. Maybe that's interesting to read afterwards.
Yeah.
It was very nice. I think you won. There's a question here in the middle in the front.
Do you want me to stand up? Okay. So you told us that information is stored in zeros and ones, and then you told us that it's probably stored in qubits, but that's still a two-level system. That's still, in some sense, discrete. Why is it encoded in the two-level system? Why not in something else entirely?
I mentioned already dice as a very different way of doing bits. So of course we don't notice that it's two-level systems. But if you want me to use Q-trits or anything of that sort, I'm doing something arbitrary. Eventually, it's not that important. And I sort of compare it to the way that people first thought about atoms. I mean, in an atom, there are many atoms that we know, but in order to derive thermodynamics, any model for that will do. So for us, it's not important whether it's two-level systems or other level systems. We just can still count how much entropy is in there. So there is a definition of entropy that's independent of the fact that it's bits or something else.
There's already the catchboxes arrived there. Yeah.
Yeah, thank you for the lecture. I had a question. You talked about multiple phenomena across many scales. You talked about the whirlpool, you talked about the cyclone, and then you showed us galaxy, and then you asked us if the physics behind them were similar. You also talk about how the physics changes in scales from, say, the ones we see as properties of air, properties of gases, to the atomic scale. So do you think the physics of larger bodies, such as the cosmic bodies, may have entirely different properties that we cannot see because we are quite small? Is there something else to that?
So people ask me, I mean, let me answer it in the following way. So what I know is that indeed the physics at large scale can be very different than what is short scale. So the predictions of this theory is not going to tell us anything about gravity that works differently here at Earth. So in order to measure it, we really have to go to these large scales. But to understand what is going on, we also have to have a microscopic understanding. I mean, this is also with thermodynamics. We have to know sort of that there's an atom picture, but then we can derive the effective physics at large distances. And it's true that different scales generally don't talk to each other very much, but we can observe the effects, say like in galaxies and so on, of this large-scale dynamics without actually having to do the experiments here at Earth. We just observe what's happening out in large distances. And just to give you a slightly other example, I mean, in order to understand what's happening in this material, I also have to understand what it's made of and what the properties are at very short scale. So there is a way in which the short scale physics does affect what is happening at large scales as well.
It's very good analogy. The sketchbook is there, yeah. The gray one.
Hi. You told us about the fact that your theory works well with results we have now. But do you know about any promising?
Oh, okay.
Oh, what? Oh, sorry. Oh.
Maybe you can stand up, then it's easier to see.
Hello.
Yeah.
You told us about that to lend credibility to your theory, you'd need some more promising predictions that could be proven true. Are there any promising predictions you've thought of so far, or anyone else has thought of, that we could test in the future or in the very far future?
I have some ideas. I mean, they have to do also with developing the theory further. One of the things that need to be worked out, which is important for what dark matter now does. I mean, dark matter has been used in structure formation, in explaining what happens in the CMB. So I have to do calculations how to explain this using my theory, and then see if there are differences between that and what dark matter would predict. So there's one problem with that. First of all, dark matter is not a very precise theory in the sense that people can assign many properties to dark matter that makes it behave in all kinds of ways. And that's been used a lot to explain any discrepancy that people see. So you are fighting with a theory that is almost morphing itself into a solution every time. But you have to make a very precise prediction, which I'm not going to do now because I feel like I have to develop the theory first to the level where I know exactly what's coming out of this, because if I make one prediction after the other without, well, being 100% sure, I should not do this. So no, I think that we have to wait. And one of the questions I'm wondering about is actually the way that dark energy behaves as a function of time. So I'm actually quite excited about data that are showing that the Hubble constant nowadays and what we predicted from the cosmic microwave backgrounds actually have a discrepancy. Other things about cosmology that starts to sort of become a little more troublesome. I think there may be ways in which this theory can do better, but we still have to wait and develop the theory to the point that we can be totally sure that we have a full, complete theory.
Thank you.
The other sketchbook is there. Maybe you can stand up. That's easier to see who is asking the question.
Yes, hello. So my question is, if the theory would be correct, for my brain it's a bit too hard to understand all the implications, but would there be anything we notice in daily life that would, so for example, once we understood satellites, then we had, it had implications for our phones and our stuff. So does it have any meaning?
You mean for things on Earth here? I mean, usually...
Yeah, for our daily lives.
For our daily life. I mean, here I think the chance is very small, but I think we have seen other examples in science where it was not totally obvious. These implications may come centuries from now. I don't know. It's certainly not my motivation to do it that way. And it seems to me, actually, it's related to the answer I gave before, that the things that I worry about, which have to do with more cosmological scales, are not going to be immediately relevant for what we experience in our daily life, except for one question. I mean, I haven't shown some of the cartoons I sometimes show in public talks, which is, why are we doing this? And it's one of those questions that I think everyone wants to know eventually, is where does the whole universe come from? That question is now being answered using the theory of the Big Bang, and it may be something that, well, you can think about. So I think that when we know more about our origin of the universe and things like this, this is something that everyone can be curious about, and in that way it may affect more people than just the scientists. I mean, that's my motivation for doing that, is very much more motivated by these big questions than making things that immediately are applicable for our daily lives.
Maybe here the theoretical physicist meets the applied physics students. Yeah, it's of course also something that the students here in Delft maybe think more about. Yeah. We have the gray catchbox, which is there. Yeah, please stand up. It's really in the middle.
Yeah, hello, thank you for the lecture. I have a question. You considered the outermost sphere of the observable universe as the surface for your information calculation. So my argument is there a possibility that if there is something outside, then outside the observable universe, then there would be a little more dark matter. But then again, if your equation is actually satisfying with respect to the current gravitational observations, then in that case we are saying the observable universe is the end of the universe. Is that true?
Well, this is still a debate. I mean, I told you something about the horizon and what's happening there. Even for black holes, people don't know whether, when we're on the outside, whether we should be talking about what's going inside, yes or no. So I say the same thing for our cosmological horizon. It's really part of the universe that we have no communication with, and nothing that's there can affect us. So I like to sort of not include it in my considerations. So I think it will not affect our physics. And for me, the fact that the universe has a finite horizon at a certain distance with a finite amount of information is actually quite essential to the ideas that I've been using here.
Can I continue on that? I have one more question.
The blue one is there. Yeah.
Hi.
Do you see it? He's standing on the side.
Yes.
Hello.
Yeah.
Thank you for the talk. My question sort of hooks into his question. You said that the boundary of the universe sort of defines the information with the amount of information within it. Does that mean that the increased expansion of the universe is directly related to the amount of entropy in the universe?
So yes. So the Hubble parameter, which is the one that determines the expansion rate of the universe, is directly related to the size of the horizon, and therefore that connection has to be made. So for me, the Hubble constant becomes a fundamental constant of the theory, very much like Einstein's, the Einstein constant, the Newton's constant. And so the density of the information or the amount of information is directly related to that constant.
But does that mean that entropy is the only factor in the increase in size of the universe?
Well, let me say just yes. I think that's
okay.
Thank you. The catchbox is now there. Yeah. Can you stand up, please?
So you mentioned something about Gerard Hooft's holographic principle.
Yes.
And that basically all information in the universe is represented at the horizon, at the surface of the universe. And since then, this has been shown mathematically to be the case for an anti-de Sitter universe. But in your talk, you also mentioned that in your theory, information is also included within the universe itself. So how do these two ideas actually compare to each other?
So the holographic principle does not state that the information is on the surface. It says that there should not be more information than the surface that could be on the surface. So it's an upper bound of the amount of information that can be inside. It's true that in anti-de Sitter space, which is a universe without dark energy, it lives on the boundary. And one of the main points I've made here is that the appearance of the horizon and the finite temperature has to do with the fact that we live in a universe with a positive dark energy. And if you want to know more about the rest of the argument, I say you would have to read my paper, because that's explained in the beginning.
You have a great evening.
I will do
and
that.
Tomorrow weekend. Maybe the catchboxers can also go to the front.
I will throw it there afterwards.
Okay, yeah.
Thanks for the very interesting talk. I was wondering, you talked about entanglement, and about information, and they say that entangled particles can transfer information faster than light. Do you have any theories on that?
Well, it's not exactly true. I mean, entanglement is a state of the two particles, and in order to transfer information, which you can do, say, through quantum teleportation, you still have to transfer a signal that goes with the speed of light. So there's no fast communication possible with entanglement.
Okay. That is correct. There's one here.
Yeah, my question was also kind of related to this one. I was wondering, what if you have this entangled particle, two particles just on the edge of the horizon, and one goes into the black hole and the other one stays out, and into to the universe? No. But yeah.
Is it actually your question?
No, it's not actually your question. But well, you have these entangled particles, and they are related, but one is on the other side of the horizon, so you have exchange of information. It's a kind of paradox, but how do you see this?
Well, they're entangled, which is not, again, exchange of information. I mean, entanglement is just a statement that an outcome of a certain measurement here is correlated with the outcome of another measurement. It's not a form of information that's being sent over. I call it sort of sometimes shared information, in the sense it's the same information that's available to both, but you cannot use it to send information.
Okay, it arrived in the front here, yeah?
Thank you for your lecture. I have a question. If we go ahead with the theory of Big Bang, so during the beginning, the universe is a hot plasma, and it started expanding, and once it started expanding, it gets cooled down, and all the plasma ingredients in the plasma start coming together.
Can I have the slides here?
Can we have the other screen?
So my question is, could you please explain what force is responsible for the ingredients in this plasma to come together? Is it gravity? Because
I really have been doing just this here. This is my interpretation of what that story is. Just look at the slide. I'm not going to answer it. I mean, for me, the Big Bang story is not believable. And it has to do with information. It has to do with the fact that the statement there is that everything emerged from something. It's a story of the universe that we like because we have been reasoning backwards. And in doing so, we have done what we normally do. And I already explained it to an answer. We have done what we humans do, is namely make things abstract, ignore information, throw it away. So we have a very simple picture of the beginning of the universe where most of the information that's there is considered irrelevant. If you would put it all back in again, the picture would be very, very different. The math may be similar, but the story is very different. And so I don't buy this. I think this is really just a story that's being told over and over again in such a way that people start believing it. And I think if you think about it logically, it's not a very logical story, actually. Nothing in other parts of physics works like this, where something can begin at a moment without having existed before it.
Thank you.
I think that's very clear. Thank you. Yeah, there in the middle.
Yes. Perhaps I misunderstood you, sir, but is it truly so that you suggest that dark matter doesn't really exist?
Yes.
Do you then also think that the same applies to dark energy somewhere out there?
No.
Clear statement.
No, for me, dark energy plays a very important role. It made the difference between the universe without the information and with it. And I used the dynamics of dark energy to explain the phenomena that we attribute to dark matter. So for me, the dark energy is the real thing that makes that thing happening. So the information I talked about is associated with that. And that's what's filling the universe. And what we observe in what we call dark matter, we think of it as a particle, and that would be sort of something else than dark energy. And so the current theory would make no connection between dark energy and dark matter. But I claim that what we observe is actually due to dark energy and not due to dark matter.
But what I mean is, like,
So
I'm
I
not
think
an expert.
we don't do the discussions,
Oh,
or do you
okay.
want to? Because I think there's so many questions, we have very little time, so
Very well.
we can continue, and then there will be drinks afterwards to discuss even further. Yeah. So I think we do 2 more questions: one blue question and one gray question. Yeah, you're the lucky blue question.
You see dark energy as composing the majority of the entropy of the universe, and, but then the other explanation has always been that it's given by the cosmological constant, which I just understand as a geometric argument, as a geometric constant.
It's the same as saying that all of the molecules in this room can be summarized by giving it a temperature, the motion of all the molecules. It's a simplification of what's going on, which effectively works very well, because for our daily experience, that temperature is a thing we care about. And the cosmological constant summarizes what is most important for that description. This is the way that it appears in Einstein's theory, but I think it's an oversimplification of the actual dynamics that is going on. So there's a lot of dynamics going on in this dark energy that is not described by general relativity.
So you're saying the cosmological constant is itself an emergent phenomenon?
That's correct. It's just like temperature is emergent in thermodynamics.
Great, thanks. So there's the final question in the back.
Do you have an alternative theory to the Big Bang?
I think I answered that question already. That's something that needs to be developed. I can tell you what my thoughts are about it. So I think that indeed the universe did not start in a short moment, but the idea of emergence is much more subtle. It means that something cannot appear out of nothing. It must appear from something else. So space and time have to be appearing from something that was already existent. Now, if you ask me what is the math that goes with it, one of the mathematical descriptions I'm thinking about a lot is called chaos. So in chaos, what happens is that you have things that are exponentially growing. Namely, it's like the butterfly effect. If I have 2 things very close by, they may end up in very different parts. But generally, when you look at this, then there are also things decaying. And some certain things grow, other things become less important. You can throw away the thing that's less important because you cannot observe it. But then you are only left with things that grow. And that's what the universe description now looks like. But if you take the entire description, you see that everything actually is preserved. Nothing really gets bigger. Actually, all of the volume, even all of the information gets preserved. So it's a much different description, but effectively, you might find the equations in there that we're now currently using to describe the Big Bang. But the theory itself will be much more complete in terms of keeping track of all of the information that's there. And, but anyway, I'm not going to speculate too much about what the math exactly looks like. This is something that needs to be worked out.
Thank you. So yeah, that was great. I think we will hear still a lot from you in from new theories. And I think if I look at this room, there are many young students that maybe look at you the way you looked at your television program when you were young. Is there any message you want to give to the students, like how they can be the next people that make great theories or do great physics?
Well, I think, first of all, you must be doing what you find most interesting with everything. I think even if you start doing research later for your master project or for anything, when you do something that you really like doing, you are much more effective and much more likely to be successful. And indeed, ask yourself what are the questions you're interested in, and what is it what you want to do. And if you go for that, I mean, I knew it when I indeed started, before I started studying, and I kept a focus on that. So if you have some idea what you really like and you want to go after, you should do it.
And focus. Thank you very much for being here. It's been great. Thank you.